Aditya, am I audible?
Sir, we will be starting in 2 minutes.
Hello.
Hello.
Yes, we are starting within a minute.
Okay.
Uh,
So do I need to press anything for the recording or just dismiss record? Yeah, nothing. No, it says dismiss.
No, recording is started right now.
That's
You can dismiss. Yeah, this is just notification.
Thank you.
Hello.
Yes, Aditya, you're audible. Yes, Aditya, you can start. Yeah, please.
Okay. Thank you. Thanks. Okay, so I would like to begin by asking that what is civil engineering or who are civil engineers? If I would quote Herbert Hoover, the former president of United States of America, according to him, civil engineering is a great profession. Why? He justifies by saying that there is a fascination of watching a figment of imagination emerge through the aid of science to a plan of paper. Then it moves to realization in form of concrete, stone, cement, and energy. Later, it brings jobs and eventually it elevates the standard of living and adds to the comfort of life. And this is the civil engineer's highest privilege. With this thought, I wish a wonderful morning to one and all present over here, distinguished guests, faculties, and all dear participants. My name is Aditya Pal, and on behalf of Applied Mechanics Department, LD College of Engineering, I wholeheartedly welcome you in this 5 days GIAN-sponsored short-term training program on design of confined machinery buildings for earthquake disaster and risk mitigation in India. So without taking any further moment, I would like to begin with our inaugural session of this program, and it gives me an immense pleasure to welcome our panel of esteemed dignitaries. We have with us today Dr. Svetlana Brizov, who is joining us all the way from Serbia. Thank you, ma'am, for joining us. Later, we also have Major Dr. C.S. Sanghvi, sir, Professor and Head Applied Mechanics Department, Government Engineering College, Modasa. He is also the convener and chief coordinator of this program. We are also fortunate to have the principal of LD College of Engineering, Dr. Rajul K. Gajjar, ma'am, to join with us. And she is the chief patron of this STTP program. We have Dr. G.M. Tank, sir, Head of Department, Applied Mechanics. Now, they say that world is full of diamonds and gems, and I mentioned these names that we are quite fortunate and blessed. Thank you, sirs and madams, once again for joining us. Now I know you all would be eager to listen from our elite panel of experts, but before inviting all our speakers, I would like to grab this opportunity to introduce you all with our college and the Department of Applied Mechanics. LDCE, Lalbhai Dalpatbhai College of Engineering, is a premier government engineering institute of Gujarat, set with an objective of imparting higher education, research, and training in various fields of engineering and technology. LD College of Engineering was established on 20th June 1948 as one of the few first engineering colleges in India. LDCE is now celebrating its entry in 75th year as India is completing its 75 years of independence. LDCE is also now equivalently celebrating its entry in the 75th year of successfully imparting technical education to aspiring engineers. LDCE offers both undergraduate and postgraduate courses in as many as 14 major departments. To add more feathers, LDCE has received prestigious NBA grant in 5 departments, and LDCE is proudly the only 5-star institute in the state of Gujarat. Being such an historic institute, LD is not only about great past and legacy, but very actively upgrading system and infrastructure as per the need of modern technical education under the dynamic leadership and teamwork of all the stakeholders. LDC has and will keep on serving this nation and its countrymen through the light of knowledge. Moreover, the Department of Applied Mechanics is a vital offshoot of civil engineering program of LD College of Engineering. Applied Mechanics deals with imparting education to undergraduate students in the subjects like mechanics of solids, geotechnical engineering, design of structures, concrete technology, design of steel structures, retrofitting of structures, earthquake engineering, and many more. The department also offers 2 postgraduate structural engineering and geotechnical engineering. Above the regular classroom teaching, Applied Mechanics department has also been involved in research and consultancy, and we have collaboration with some major firms pan-India for testing and research purpose. Now, in this STTP program, we have all the participants joining across different parts of India, or rather, I would say from different parts of the world. So let us have a short virtual tour about this campus so you can get more idea about it. Pardon us for a little connectivity issue we are facing over here. We'll play the entire video with voice and proper video without lagging in some moment. But before that, to continue with our program, I would now like to invite Dr. GM Tank, sir, the respected HOD of Applied Mechanics Department, to deliver a welcome address. Sir has done his PhD from IIT Roorkee and has got a mammoth teaching experience of more than 23 years. Without taking much moment and inviting the dignitary himself to take over the session, respected sir, please hand over to you. I hand over to you.
Dear all, a very warm good morning. And already a very warm climate in Ahmedabad here. So, warm good morning to one and all who are present here to attend this one of its kind of short-term training program entitled Design of Confined Masonry Buildings for Earthquake Disaster and Risk Mitigation in India, organized by Applied Mechanics Department under the aegis of GIAN, the global initiative of academic networks. Applied Mechanics Department has a distinguished and technically well-versed faculty imbued with a sense of commitment and sincerity. As the head of department, it is a matter of immense pride to bring to you the multifaceted activities and achievements of the department. The department offers UG program with electives in domain of structural analysis and geotech, and 2 postgraduate programs in structural engineering and geotechnique. The strength of programs offered by this department lies in a strong technical and field experience of the faculty who are involved in research and consultancy over and above their regular teaching. In regular teaching, they actively involve the students through quizzes, models, field exercises, and site visits to make learning an enriching experience. Department conducts an array of activities around the year. These include short-term training programs, expert talks, industrial visits, technical competitions, etc. All the activities are carried out with a larger aim of enhancing the industry-academia collaboration to reach out a larger section of the technical stalwarts and to tap the academic and co-curricular acumen of students in terms of fundamental knowledge, team spirit, leadership skills, presence of mind, creativity, and zeal to innovate. The students of the department are equally diligent with when it comes to academics as well as their participation in technical events. The testing and consultancy activities carried out by the faculty members of the department helps in revenue generation for the institute. Applied Mechanics Department has established the Earthquake Engineering Laboratory, which is first in the Gujarat state. I convey my sincere best wishes to the convener and coordinators of the STTP and hope that this will make a valuable addition in terms of knowledge gain for the participants. My sincere thanks to expert speaker of the STTP, Dr. Svetlana Brzezev, for having spread her precious time in meticulous planning of the lecture modules to be delivered throughout the 5 days. Wish you all a happy learning. Thank you. Thank you so much.
Thank you, sir. Thank you so much for your kind words and warm welcome for all our participants. Moving further, now this entire event is organized under the aegis of GIAN, that is Global Initiative of Academic Networks. So now I would like to invite Dr. MC Chudasama sir, who is the GIAN Program Coordinator of LDCE, to give an overview over this GIAN program. Sir has also got the vast experience in the field of teaching, and he is a professor from Electrical Engineering Department. Most welcome, sir. Over to you.
Good morning, Aditya. Am I audible properly?
Yes, sir, you are absolutely audible.
Okay. So, good morning, respected Principal Madam, respected Dr. Svetlana Brezev, the foreign expert for this STTP, respected Sanghvi sir, Kiran Tak sir, Gopal Tak sir, Professor C.D. Patel, co-coordinator of this program, all the faculty friends, head of the departments, participants from various institutes, industries, and all other research fellows. Good morning and welcome to all of you. As a local coordinator for this GIAN program at LD College of Engineering, it's my pleasure to welcome you all. The Global Initiative for Academic Networks is a program sponsored by Ministry of Education, Government of India. The coordinator for this program is IIT Kharagpur at national level. We are getting the funding through the central government through IIT Kharagpur, and all the courses are being monitored by IIT KG. I'm proud to share with the audience here that LD College of Engineering and one more institute in the state of Gujarat are the only institutes selected under this GIAN scheme, since it has some tough criteria, including the accreditation of various programs and several other criteria. So it's a pride moment for all of us that we are the institute in Gujarat who are selected under this prestigious GIAN scheme. The main objective of the GIAN program sponsored by the Ministry of Education is to promote collaboration of our institutes, Indian institutes, with the foreign universities, foreign institutes, and to get the advantage of the knowledge base from the expertise of their faculties. And as a result of which we are conducting this STTP today. I'm also happy to share with the audience that LD College of Engineering has already conducted 4 STTPs, and this is the 4th one in the series. 2 STTPs are already conducted successfully by the Computer Engineering Department. 1 STTP is already done by the Mechanical Engineering Department of this institute, and this is the 4th one which is being conducted today. I would like, at this moment of time, I would like to congratulate the team of Dr. C.S. Sanghvi, C.D. Patel, and all the faculty members who have nicely managed the event. And I would like to wish grand success to this event. I would like to appeal all the participants that you take maximum advantage out of the STTP, and please share it with the colleagues, with the students at your level, so that the objectives are served for this STTP. Thank you and wish you all the best of luck. Over to Aditya.
Thank you so much, sir, for your encouraging words and detailed information about the programs that are conducted and that are done under the GIAN. So now I would like to briefly introduce the context of this very course for which you all have joined and are eagerly waiting to enhance your knowledge on this subject by listening to our expert. So looking at the immense scale of devastation and loss of human life in the recurring disasters in various parts of the world, one of the key areas needing attention is now how to make our buildings disaster resistant. The use of modern reinforced concrete buildings technology have resulted in significant human and economic loss in earthquake in many countries. And we all are familiar with the devastating Bhuj earthquake in Gujarat 2001 and the earthquake in Gorkha, Nepal, that is 2015. There is need to explore alternative construction practices such as the one which we will be discussing in this course of 5 days, and that is the confined masonry, which can be implemented even under the unfavorable field condition. For throwing more clear light on the outcome of this program, it is my honor to invite our dignitary and personally an inspirational figure to me as under his guidance, I completed my graduation. I would like to welcome Major Dr. C.S. Sanghvi sir, the professor and head of Applied Mechanics Department, Government Engineering College, Modasa, for giving us the overview of this training program. Sir has got the professional experience of more than 30 years. Sir, yes, sir. Just a few seconds I would like to take to introduce Sanghvi. I won't go in much detail. He has got a long list of introduction, but sir has got several accolades Sir has also published various books on technical subjects. And we have the very one thing which I would like to emphasize on this particular thing about Sanghvi sir is we have a unique in-house earthquake engineering laboratory at LD College of Engineering, which is the pride of LD College and one of the first of its kind in entire India. And and all the credit and thanks goes to the leadership of Sanghvi sir, under whose leadership this entire laboratory was established. So I won't take much moment ahead, and I'll hand over to Dr. C.S. Sanghvi sir to deliver. Thank you, sir.
Thank you, Aditya, for the nice introduction. And the earthquake lab cannot be constructed without the teamwork. So all the faculty members of Applied Mechanics department have contributed a lot for the development. Very good morning to one and all. Respected Dr. Svetlana Brezheva, who is adjunct professor at British Columbia University, Canada. She is also course expert and chief guest of this inaugural function. Dr. R.K. Gajjar, principal, LD College of Engineering and chief patron of the STTP. Dr. Chudasama, Dr. Tak, my dear colleagues and dear participants and volunteers. It is my pleasure to welcome you all on behalf of Applied Mechanics Department of LD College of Engineering. Dr. Tak has given a brief profile of Applied Mechanics Department. I want to add something to it. The department is very actively working in the area of earthquake engineering, and department has developed a unique low-cost instructional earthquake engineering lab setup with the help of GSDMA, Gujarat State Disaster Management Authority, which requires only 7 lakh rupees to develop. Institute is considered as a resource institute in the area of earthquake engineering. Department has also carried out a project of library and laboratory development in the area of earthquake engineering with the help of GSDMA. Now in Gujarat, more than 50 institutes have installed a similar laboratory setup at their institute. Department has coordinated more than 60 training programs with the help of GSDMA, GIDM, Gujarat Institute of Disaster Management, and Road and Building Department in the last 15 years for the government engineers, for the professional engineers, architects, admin officers, masons, and many other people. Department is involved in many activities related to the capacity building in the area of earthquake engineering. Recently, during the Corona pandemic, department was involved in developing a low-cost actuator with 50-ton capacity and biaxial shake table with the 2-ton capacity. The cost of this product is very high in the market, but this product is developed, whose cost is less than 20 lakhs, which is remarkable. Department is continuously working in this area. Now, question will arise: why this STTP on design of confined machinery for earthquake disaster risk mitigation in India requires? We know that India is prone to severe earthquakes, and we have seen many earthquakes at a regular interval of 3 to 5 years from 1988. 1988, we have a Bihar-Nepal earthquake. 91, we have Uttarkashi. 93, Latur. 97, Jabalpur. 2001, Bhuj. 5, Kashmir. 11, Sikkim. 15, Nepal, and many others. So India has observed 5 great earthquakes in past. But the most important observation is that after 1950 Assam earthquake, India has not observed any great earthquake. It means lots of energy had been stored, which may bring a big earthquakes in future. Over the years, these earthquakes have caused extensive damage to the life and property and have adversely impacted the economic development of the nation. We know that the earthquakes do not kill people, but unsafe buildings do. We have seen the devastation during the 2001 Bhuj earthquake. We have seen the maximum damage and collapse of the unreinforced masonry structures. 13,805 people died during the Bhuj earthquake, out of which almost 75% people died because of the unsafe, unreinforced masonry structures, because their failures are brittle in nature. And therefore, there exists a need to improve performance of unreinforced masonry structures. And it can be done by another construction technology known as confined masonry. Chile, Mexico, and many other countries are already exercising this technology. They have already used this technology, and enhanced performance of these masonry structures had been observed in past. Till 2020-22, no Indian code or Indian standard code available in India. But now Indian standard code for confined machinery IS 17848 is published in 2022 for the first time in India, and therefore there exists a need to train the faculty members and the students in this area for the benefit of the construction industry. It is really a moment of pride for us that this is the first training program in India after the development of the code. And I'm very happy to say that one of the main contributor in developing this code, Dr. Svetlana Brezev, who is international expert in the field of earthquake engineering, has given her consent to conduct this training program as an expert foreign faculty. This program was planned in 2020, but because of the corona pandemic, it was not possible to conduct in last 2 years. Generally, this course is conducted in the offline mode, but because of this pandemic, the IIT Kharagpur has given a consent to organize it on online mode. Dr. Svetlana is very humble, patient, and very firm to conduct this training program. As a result of this, we are able to organize this training program now. Very interesting topics are covered in the schedule. I am sure that it will be very useful to you. We know that technical fraternity has to ensure earthquake safe design and construction practice in the country. Making earthquake safe society is a very long process, and it requires a capacity building in this area. US has started the capacity building program in way back in 1970, and it is still going on. We haven't started yet. That is the problem. So just imagine how much time we need to reach the similar level of preparedness. I am sure that this STTP will give you this opportunity. You will enjoy this STTP, and this program will help in enhancing your knowledge to contribute in capacity building process in future. Dr. Svetlana is constantly providing us guidance for earthquake safety since 2011. She visited LDCE in past and guiding us always. Thank you very much, ma'am, for your support. I'm very much thankful to principal, ma'am. Yes, ma'am. Thank you. I'm very much thankful to our principal, ma'am, who is constantly encouraging us and supporting us to do various activities. It may be academic or it may be a co-curricular activities. She is very supportive, and therefore this event is taking place. I'm very thankful to GIAN officials and Dr. Chudasama for giving us this wonderful opportunity to coordinate this STTP. And I'm thankful to Dr. Tak, who's the head of the Applied Mechanics Department, for hosting this STTP. I'm thankful to Professor Hansor and Professor Siddhi Patel, who are the co-coordinators of this training program, and they are putting a lot of effort to make it successful. Thank you very much to all the experts, participants, volunteering faculty members, and the students. Thank you once again. Jai Jai Karvi Gujarat, Jai Hind. Over to Aditya, please.
Yes, sir. Thank you. Thank you very much, sir, for projecting the dire need of the use of confined machinery to our participants and what they would be experiencing in this upcoming 5 days of session. It was the great opening address for all the participants. Thank you once again, sir. Now, moving ahead, I will be obliged to welcome Dr. Rajul K. Gajjar, ma'am, the principal of LD College of Engineering and the chief patron of this training program. Before that, I would like to briefly introduce the principal, ma'am, to all of you. Ma'am has a colossal experience of more than 39 years in engineering profession. Ma'am completed her undergraduation and post-graduation from the LD College of Engineering, Ahmedabad, and her PhD from MS University, Baroda. Ma'am has published numerous national and international research papers, along with 3 published patents named after her. Ma'am has authored several books and has supervised numerous postgraduate and doctoral students. Among major national awards, ma'am has been bestowed with eminent civil engineer for outstanding contribution to engineering by Honorable Chief Minister of Gujarat. She was awarded by Honorable HRD Minister at International Vibrant Education Summit for Best Innovation Practice and by NASCOM and Higher Education for Eminent Leadership. Now, this list will be quite long, but I know the modesty of our ma'am that she is always eager to address and interact with the participants in such programs rather than mentioning her unending list of achievements. So without causing any further delay, I would like to invite Principal of LD College of Engineering, Dr. Rajul Gajjarman, for opening address. Over to him.
Thank you, Aditya, for the kind words and sparing me those lengthy descriptions. A warm welcome to Dr. Shwetlana, all my colleagues, Dr. Chaitanya Sangvi, Dr. Tang, Dr. Hansora, Dr. Chintan. It is a sort of a coming together of a family of like-minded people. And it's such a pleasure that all of these are, even though spread across the world, we are connected and we are together in the different time zones. To carry on the conversation with which Dr. Sangvi started, it is all about how we look at our preparedness for the disasters that are not just an event which will come in the future, that has continuously reminded us that we are vulnerable. The situation that has again and again erupted across India, it is across the world, but let me be very specific geographically also, across India and also across Gujarat. It has been a great concern. We are really very thankful that experts like Dr. Shwetlana, Dr. Sudhir Jain, and a long array of all our friends and colleagues from the IITs who have continuously worked with us, tried to create a structure, a system, a systematic approach through the government, through the municipal corporations, through the codes. And this is a huge, humongous effort which cannot happen without the expertise of mentors like Dr. Shwetlana, who are with us today. So I will reiterate that yes, preparation is very much needed. As repeatedly mentioned in many such conferences and workshops, what happens is that when a disaster occurs, there is a huge UN cry. Everyone is on their toes. All the policymakers, all the people who can do the management, the middle level management people also, they are on their toes, and everybody feels that yes, something has to be done. And then gradually there is this whole process in which the mindset occupies the other priorities, and there is a little bit of a sort of a dispassion that comes up that okay, fine, we have ridden the worst time, and the memory then elapses into what really needed to be done. Coming back to the efforts that experts like Dr. Chaitanya Sangvi, Dr. Sudhir Jain, and all the experts from IITs have helped us do is that we did have a separate course in earthquake design. And then gradually, with all the curriculum and the credits and the systems that were coming into place across the world, there were model curriculums, and we were asked to reduce the core and bring in more electives. So the best thing that we could do was that, and that was also something that has brought in a lot of expertise into our design courses, is that we created within the design courses themselves the earthquake resistant design, so that everyone in the core has to go through these courses. They are across the board, and rather than offering as electives or offering as separate courses which people might take or people might not take, choose to take, is something which is always an ongoing conversation that we have been doing. So there are many ways in which we can keep creating a structure. A strong structure is definitely needed, starting from the curriculum, starting from the academicians, going up into research, which Dr. Svetlana has done humongous amount of research in masonry, and very early on, when even I was doing my PhD, I bought the books which Dr. Svetlana had written, and I am one of the followers since very early on, is where I connected with Dr. Svetlana. So I look forward to this entire training, wherein we'll go through and we'll once again, each of the teachers, each of the participants, each of the students, please carry back with you a strong message that we are the people who have to create a safe world. We are the people who will be technologically there to create the systems. There are management issues, there are implementation issues, but let that be the domain of the policymakers. As far as we are concerned, we have to make every student, the last student on the campus, aware that they are responsible to avoid disasters. Their designs, their foundation, their technological intervention is what is going to bring a safer world to the citizens at large. This is what we have to, the last message and the strongest message that should go out every time we talk about whether it is earthquake or it is cyclone or it is a tsunami, but we have to be prepared to address it technologically. Thank you very much. Wish you all the best.
Thank you so much, ma'am. As always, your words have been quite encouraging and motivating and quite informative for all the participants. Thank you once again for allowing us the permissions to organize this STTP program and joining with us today. Thank you, ma'am. Right, so moving further, it gives me an immense sense of pleasure and pride to invite our distinguished and international speaker and course expert, Dr. Svetlana Brazev, ma'am. I would like to give the brief introduction about ma'am. Dr. Svetlana Brazev has more than 30 years of consulting and research experience related to structural and seismic design and retrofitting of masonry structures in Canada and several other countries. Her research has been focused on seismic behavior and practical design and construction issues related to masonry structures. She served as a member of technical committee responsible for developing current Canadian masonry design standard and is a member of technical committee responsible for developing Eurocode 8 provisions for seismic design of masonry buildings. Dr. Brazev served as a director and vice president of EERI, a director of Masonry Society, and is currently a director of International Association of Earthquake Engineering. Dr. Brazev has co-authored 2 books related to design of masonry structures and a textbook on design of reinforced concrete structures and numerous papers and publications. She has been conferred with plenty of awards, which includes Outstanding Achievement Award of Global Earthquake Model in Italy in 2016, Honorary Professor, International University of Innovation Technologies in Kyrgyzstan in the year 2016 again, the Fellow of Engineers Canada in 2015, Outstanding Paper Award, that is 12th North American Masonry Conference, USA in 2015, Teaching Excellence Award, British Columbia Institute of Technology in 2011. I guess that we would need an additional session completely if I would complete the entire accolades and achievement list of Dr. Svetlana Brazev. So I won't take much time ahead, but I would like to highlight this key point to our participants that the first IS code for confined machinery has been published last month. And this is the very first training program on the very topic after the code's launch. And Dr. Brazev has been the pivotal member of the committee, which is responsible for publishing this code. So who is better to explain about the architecture better than the architect herself? Please welcome Dr. Svetlana Brazev. Over to you, ma'am.
Hello, thank you very much, Professor Paul, for a very nice introduction. Thank you to all colleagues at LD College. I'm very sorry that I'm not with you today, but it has its pros and cons. It would be very nice to be in India after the onset of COVID again, but on the other hand, we have opportunity to have more participants from all over who wouldn't be present personally, who are now online, and that gives us some other benefits. In any case, I want to go long since we have many lectures ahead of us in the course. I'm particularly pleased to talk on this topic since it is a circle for me with my association with Masonry in India. My association with Masonry in India started in 1989 when I was at the University of Roorkee and was invited by Professor A.S. Arya to work on PhD thesis with him. I was a visiting scholar at that time, not intending to do a PhD in India. And it was related to masonry and seismic resistance. It was on base isolation of masonry buildings. And I am very happy that it continued my interest in masonry and ability to be engaged in India continued all this time. And it culminated with my work in the confined masonry and promotion of the technology and development of code, which, as you know, has been published last month. I believe that masonry is very important for India. It's important for the whole world, but particularly in India, majority of buildings are of masonry construction in spite of rapid growth of concrete structures. And I believe that the engineers must know how to design masonry. Masonry has been fully marginalized because of the lack of modern codes and in India for many years. And I believe this is a great opportunity to reintroduce masonry in a modern way, in the same way as we treat other materials such as concrete and steel. So I believe this course has a very important role because it will educate future masonry experts in confined masonry who will spread the knowledge on this topic to their students, to their colleagues, classmates, and that is a way to launch this technology, which has now all conditions are met, all the stars have been met because the code is being issued, and there is a perfect circumstance for future application. I hope that the materials we will be sharing with you will be useful, and I hope that you will enjoy the course. Thank you for being there, and I would like to congratulate LD College and particularly my dear colleague, Professor Chaitanya Sangvi, for being such a great pioneer in earthquake engineering education and for pushing this agenda for many years and achieving great results. And I wish to continue success in this field. Thank you very much.
Thank you. Thank you so much, ma'am, for your kind words and the brief introduction. It is always a pleasure to have you. And it's unfortunate, as you also mentioned, that we could not meet in an offline mode, but we'll do with the best which is possible with us. Once again, thank you for joining with us. Right. So this brings us to the closure of our inaugural program. We are indebted to all the revered dignitaries for giving us their invaluable time. I would like to once again extend my heartiest gratification to Dr. Svetlana Brizev ma'am for accepting our invitations and agreeing to deliver a session in this program. I'm also heartily thankful to our principal, Dr. Rajul K. Gajjar ma'am, for her presence and enlightening us with her kind words. I am thankful to Mr. M.C. Chudasama sir for his vital presence and information about GIAN. I am also thankful to all the head of departments of different branches of LD College of Engineering for attending this session, as well as I would like to thank Mr. Dr. C.S. Sangvi sir and Dr. G.M. Tak sir and all the faculty members of our Mechanics department for being an integral part in this program. Not having been without owners, Professor Chintan, assistant professors of Mechanics Department at the College of Engineering, Ahmedabad. And last but never the least, I am grateful to all the participants for these sessions, which I fully will assist to enhance your knowledge on this confined machinery buildings or this irrigation. And our session, I would like to request all the participants to please turn on your cameras for a while. It was a tradition when we were organizing our offline mode STTPs that we would have a group photo. As it is not possible in an offline mode, will try to take the group photographs. You know,
Yes. All the participants and experts, please switch on your
virtual
cameras.
with the help of a screen. So I request all the participants to go on.
Maybe you can write it in the chat box, Aditya, so that everyone can read it also.
Yeah.
Switch on your camera.
Yes, Aditya. Please, all the participants, please switch on your camera, and we take a group photo with a smile. This is an online program, so this will become a memory for all of us.
Aditya, you too. Okay, thank you, Dr. Svetlana. We'll be there with you, listening to you. Chaitanya, you are always there, the backbone. Dr. Tank, Aditya, Dr. Hansura, please keep up with this. Thank you.
Thank you. Thank you, ma'am.
Thank you, thank you.
Thank you, sir. I will take your leave.
Yeah. Yes.
So we are staying in this session right now. I can share my screen if that is okay.
Yes, ma'am. Yes, ma'am. Yeah.
Yes, ma'am. Yes, ma'am.
So we are starting our first session, and Dr. Brezev will start this. So please. It is visible, ma'am. Yeah.
Can you hear me well right now?
Yes, ma'am. Yes, ma'am. You are absolutely audible.
Okay, that is excellent. Thank you very much. So our first lecture is on an overview of modern masonry building technology. It will be about an hour. After that, since we are running late, we can have a few questions, and we'll continue with the second lecture, and maybe more questions will come after the second lecture, and that will conclude the morning session. So in this lecture, in this first lecture, I would like to give an overview of key components of a masonry building, and then discuss different masonry technologies, starting from unreinforced masonry, nominally reinforced masonry, reinforced masonry, and finally confined masonry, and a little bit a few words about comparison between confined masonry and reinforced concrete frame technology, which is very similar on the first sight. So key components of masonry buildings are masonry walls, and this is a load-bearing system. So, but there are load-bearing or non-load-bearing and non-load-bearing walls. Non-load-bearing walls carry only self-weight and minor any loading, any additional loading, no additional loading practically, whereas load-bearing masonry is what we are designing as structural masonry, which carries both gravity loading and lateral loading. It is a structural system in the same way as the frame is a system. So horizontal structural components are very important in masonry buildings and influence their behavior. And these are floors and roof structures. We know them as, in this course, we'll be mentioning them as diaphragms when resisting lateral loads. So even though it is floor, we will call it diaphragm for this. So this is a typical masonry building with lots of walls in both directions, as you can see, and then floors. And in the building, it is very important to have a very good integrity, as we were discussing, that is good connections between the walls, good connections between walls and floors and roof. And in any case, it is a completely different system than reinforced concrete frame. And for those who are familiar, and used to design frames. In the first stage, it may be a bit more unusual. I wouldn't like to say complicated. Everything is maybe complicated, but we would like to try to make it simple and understandable in this course. First masonry technology that we're going to discuss is unreinforced masonry, or URM. In the technical literature, very often, instead of saying unreinforced masonry, it's used URM. And I like to use it just for a shortcut. So these are masonry wall structures without any reinforcement, in the walls, without horizontal or vertical reinforcement. There are millions of existing unreinforced masonry buildings around the world. Many of them are in India, and since India accounts for 20% of world's population, many of these buildings are in India, but in any other country in the world, we do have unreinforced masonry, since this was the technology that has been practiced from ancient times until practically this century. So in masonry, and we'll talk tomorrow about masonry materials, we have various masonry units. Unit is not SI unit like meter or versus imperial unit. In masonry, unit is the building element in masonry, and that could be stone or adobe block or clay brick or block or concrete bricks or block. So what I wanted to say is that with unreinforced masonry, we can use all kinds of masonry units, and historically, there are many stone buildings, there are many adobe or unburned clay or mud buildings and so on, and they are all used in unreinforced masonry. And in general, unreinforced masonry these are some examples from India. Expect the right photo. Left photo is from a publication by Professor Murthy, I believe it's published in Gujarat on confined masonry, and the right photo is I took in, it was in Maharashtra after the 1993 Kilari earthquake. I worked in rehabilitation of the area affected by the earthquake, and people were building new brick masonry buildings with of course seismic provisions according to IS 4326. But these are typical brick masonry buildings all in India. In other countries like USA, for example, there are some outstanding examples of unreinforced masonry in relatively modern times, let's say from 19th century, more than 100 years old now. This is one of the tallest unreinforced masonry building, so-called skyscraper, which is 16-story high, and it is built in Chicago, USA. It's called Mondarock Building. It's still standing there today. It had unreinforced masonry walls, which are 6 feet or 1.8 meters thick at the base, and the thickness decreases to the top. When the building was constructed, there was such a very negative publicity, and media newspapers were claiming that it is going to collapse within 2 or 3 years, but building is still standing today. Unreinforced masonry is very good technology, and as I said, it has been used for centuries or for millennia. But it is good for gravity loading when there are no earthquakes, when there could be winds but not earthquakes. And Chicago is one of those areas. It does not have seismicity in there, so that's why it is no problem. However, on the west coast of US, in places like Washington State or California, there are frequent earthquakes, and unreinforced masonry has been very badly damaged in those earthquakes. Traditionally, these are some photographs from the 2001 Nisqually earthquake which affected the center Seattle area. There were many unreinforced masonry, older unreinforced masonry buildings, some of which have not been, many of which have not been retrofitted for improved seismic resistance. This is an example of the buildings where you can see that the top portion collapsed. These are parapets, so load bearing the building remains standing, but the buildings are it was very badly affected. Similarly, similar photographs were available after the earthquakes in California, where this has not been. So reinforced masonry construction, because of the issues or the poor performance of unreinforced masonry in US, particularly in the 20th century. It was the 1933 Santa Barbara, California earthquake, where many school buildings were of unreinforced masonry, and they actually were badly damaged or collapsed. There was a practice, there was a decision on the government level to introduce reinforced masonry, and that practice started after that earthquake in US, or specifically in California. And to this date, in US, most masonry buildings that have been constructed are of reinforced masonry, and but in some places it is still permitted to use unreinforced masonry if there is a very low or no seismicity. There are some examples of masonry buildings from North America. These are from Canada, old unreinforced stone masonry buildings in Quebec and in Vancouver. So many of these, most buildings have not been retrofitted, and even though they're in high seismic hazard areas, but there are no frequent earthquakes, even though hazard is high. The other technology, so in this course, we of course are not going to talk about unreinforced masonry anymore. The next technology is called nominally reinforced masonry. It's not generally known in the literature as nominally reinforced. It is in the code, for example, in Canadian code, it is mentioned as nominally reinforced, but in Indian codes doesn't exist the term. So what do we mean by nominally reinforced? We would say it is mostly unreinforced, but some reinforcement is provided at critical locations in vertical and or horizontal direction, such as vertical reinforcement at door and window openings and at wall intersections, and reinforced concrete bands at plinth, lintel, and or floor level. So this is the type of masonry that has been practiced in India according to the codes until now. And the idea of this technology, and any actually technology for reinforcing masonry, is to achieve so-called box action of masonry, which is critical for good seismic performance. So box action is when we have, let's say, a simple structure of 4 walls, and if it is subjected to seismic forces, as you can see at the left drawing. On the left drawing, you can see that if the walls are not connected, there is a significant, I would say, out of plane movement of the walls, and possible collapse and separation of walls at the intersections. And if there is nothing on the top to hold them together, there is definitely a possibility of collapse at the higher earthquake levels. However, if the walls are somehow connected at the intersections, so the walls at the corners, and if there is a rigid floor or roof at the top, there is a good chance, a possibility for box action and integrity. So the purpose of this nominally reinforced masonry is to achieve all that, to achieve this integrity, which is a critical characteristic of good masonry performance. And it is these horizontal bands which have been introduced in India and have been first seen in application after the, I believe, Assam earthquake at the end of 19th century, and have been developed or have been seen. The good performance has been observed after the earthquake, but it took a number of years to get into the codes. And it is a part of India code for IS 4326 and IS 1893. In any case, the function of this belt or horizontal band is to act like a belt. And these are the provisions that are now present in India with nominally reinforced masonry, horizontal bands at lintel level, at floor level, roof level, could be seal level and plinth level. And they are mandatory for seismic zones, for masonry construction seismic zones of India. Unfortunately, this has not been always applied, and for that reason, in many earthquakes, including the 2001 Bhuj earthquake, buildings that did not have bands masonry buildings performed poorly, but buildings that had bands performed much better, even though earthquake was very strong. These are some examples from Iran. It's not only in India that this technology has been used, it's used in other countries, but in India, it has been included in the codes. In some other countries, it could be an effort after earthquakes, such as in India, in Iran, it was after 2003 Bam earthquake, which caused many collapse of significant number of buildings with masonry buildings, and particularly they had, even though they were houses, they had the domed roofs. In many cases, the walls were of adobe construction. So after the earthquake, they introduced bands in post-earthquake rehabilitation. These are some photographs from Kashmir after 2005 Kashmir earthquake in Pakistan. Again, bands. And these are some photographs from India or Pakistan after the earthquake. So bands were used particularly after the earthquakes, but oftentimes they're not introduced in new construction, unfortunately. The good testing has been done in the different scales in different parts of, I would say, that region where India is. One of the examples of important testing programs of buildings with bands was in Pakistan after the, as I said, after the 2005 Kashmir earthquake, where the researchers at NED University in Peshawar tested models of stone masonry buildings with concrete floor on the left, roof, pardon me, and they were on left side is unreinforced building with concrete floor. On the right-hand side is building with bands and with wooden roof, which is common for that region. This building has horizontal bands, plus it had vertical elements. In actually the corners, it had something like confined masonry. At the end of this presentation, just I wouldn't like to interrupt, I have videos of testing of this that was done on shake table at the University of Peshawar at very strong earthquake loading. So as you can see, the final results, building that had bands, had some experienced some damage. You can see a part of the, on the right-hand side, a part of the wall is missing, but it did not collapse, whereas the building with concrete floor roof, but without any reinforcement, collapsed with at the same level of earthquake shaking. I here included a reference of the paper that was published related to that testing, and by Professor K. Sarali. He is the primary author. In India, there were efforts to also reinforce vertically brick masonry, but this is a bit problematic and challenging for practical implementation. This is so-called Quetta bond, which is well known in India and was developed in India, the territory of India at the time, and it enables enables construction of vertical reinforcement in so-called pockets of between the masonry, between the bricks, which are filled with mortar. I had experienced construction of or witnessed construction of these pockets for my PhD thesis, which was reinforced masonry with vertical reinforcement at the corners. And it was very, I think, time-consuming for masons and a bit complicated because of the cutting of numerous cutting of bricks. But it is possible to provide vertical reinforcement in brick masonry. In any case, this is one of the rare examples. It is considered to be difficult to provide vertical reinforcement brick masonry. Horizontal reinforcement in the form of bands is not a problem, since these are reinforced concrete elements. These are examples which are part also of Indian codes, how to provide these pockets with vertical bars. So it is usually a single vertical bar which has no confinement. It is just embedded in mortar, not concrete. And these are relatively small pockets on the size of, I would say, 10 by 10 centimeters. So only one bar could fit there. So, this, I would say, to conclude on nominally reinforced masonry, we are not going to again discuss that, since it is not the topic of this course. It's definitely much better than unreinforced masonry. and it has its own benefits. It does improve performance in earthquakes. It was shown in Indian earthquakes. I've seen also buildings in Kilari area in Maharashtra, which was affected by the 1993 earthquake, which had bands. It was undamaged in that 6.2 earthquake or so, where all surrounding stone masonry buildings or unreinforced masonry buildings collapsed. So it was in the epicentral area of the earthquake. It is a very well-known building at that time at least. For that reason, for the reason of limitations of nominally reinforced masonry, there is a technology called reinforced masonry. And we should be careful what we call by reinforced masonry, because it has been established on a global scale that reinforced masonry means masonry with internal horizontal and vertical reinforcement, and that type of masonry has been practiced in North America, US, Canada, and then Australia, New Zealand, UK to a certain extent. It is not much practiced in Europe, but I would say North America for sure is the area where it has been practiced significantly. So it is, and I will show it, it is somewhat limited by the type of, or defined by the type of masonry units. As I mentioned, the term unit, as I said, it's masonry element. In this case, there are hollow concrete blocks, which are not usually needed to be able to construct reinforced masonry. So that it is defined as masonry wall construction in which reinforcement is embedded in such a manner that two materials act together in resisting any forces, applied loads. Reinforcement resists tension while masonry resists compression. So it is same as reinforced concrete in reality. In reinforced concrete, we have reinforcement which resists steel reinforcement, which resists tension, tensile stresses and forces, and concrete that resists compression. In this case, it's masonry that resists compression. Reinforcement is usually in the form of internal steel bars, which are grouted into masonry units or laid in horizontal mortar courses. Here are some examples of that masonry construction. You can see hollow concrete blocks. And on the left left photograph, you can see this horizontal reinforcement, which is in the form of ladder. That is not the main horizontal reinforcement. It is just one form of horizontal reinforcement. Then you can see in the middle photograph shows mason applying mortar in this on the vertical masonry joints. And then you can see a mason laying a block. These hollow concrete blocks are pretty heavy. Weight of one block is about 15 kilograms. So they're much heavier than bricks, which are about 3.5 kilograms or so. So this is a drawing that shows schematically how this reinforced masonry is used, how it can be constructed. You can see vertical bars in these hollow cores or hollow cells of these blocks. And around it, this shaded area is concrete. It is actually grout, but it's not mortar. It is like a micro concrete. So small size aggregate is there. And horizontal reinforcement, two forms. One is this ladder type reinforcement with the wire, small size wire like 3 mm. And that is called joint reinforcement because it is embedded in masonry joints. And then there is a other type of reinforcement which is called bond beam reinforcement, which is the same type of bars like vertical reinforcement. And these are the same bars that are used for, let's say, reinforced concrete construction. Could be 16 mm bars or 20 mm bars, that kind of size, or 12 mm bars, for example. So, so these are some examples of that, and this is the type of masonry is practiced exclusively in North America. No other form of reinforced masonry is used. You can see here a mason placing vertical bar, which has to go through entire wall height, and then yellow colored on the right, on the left side drawing are these horizontal bars. And this red shows this area which has been cut in the blocks in order to enable continuity of horizontal reinforcement. On the right-hand side, you can see that the wall after grouting, you can see vertical bars at a frequently spaced. So Please note here that these bars are not only at the wall, at the door or window openings and wall intersections. They are regularly placed similar to reinforced concrete shear walls. So they're placed at close spacing, and the spacing and size of bars is determined by design. I did not mention here a reference I might share with you if you are interested. It is a free download. If you are interested in this form of construction, I have co-authored one of the books on the design, seismic design of reinforced masonry for Canada, according to Canadian codes, and it is available free of charge. And that could be maybe a reference for those of you who are interested in this topic. I will share that as a link for that. So here you can see bond beam reinforcement. You can see how the blocks have been cut to receive this reinforcement. And you can see ladder reinforcement, which can be now clearly seen. There's a very small size bars. And this bond beam reinforcement is Tor steel, same as vertical reinforcement in reinforced masonry. So it is practically the similar system like reinforced concrete, except there is no need for formwork, since the blocks already create a formwork for this construction. So it's very practical and cost effective, since formwork costs have been saved. This is a final photograph of this. And this is how in vertical section of elevation of a wall looks like. You can see the shaded areas which show locations where the bars are provided. And you can see that there are quite a few bars in vertical as well as horizontal direction. Grouting in this reinforced masonry is, as I said, micro concrete, which shows, this photograph shows an early application of grouting with a bucket, and it was from the end of 19th century. So it is from 1868 from USA. It is a cementitious mix. Grouting is cementitious mixture. Grout is a cementitious mixture used to fill cores or cavities in masonry construction. So, so you can see how it looks like in modern masonry construction in Canada, USA, and other countries. Grout is usually placed by when a truck comes, and the grout is manufactured in a truck and then placed by a hose in the masonry, pumped into the wall in the same way as concrete would be poured. And you can see here the process of grouting. So this explains this technology, which is very efficient and used widely in some countries, but is not used in most of the world. I would say would not use this reinforced masonry in this form like it is used in Canada, USA. Now I think there is a growing use of it in Mexico as well. I think that is the end of this. This is an example of reinforced masonry construction in Canada. It is a school building, and you can see an interesting example of a curved wall which can be constructed using this technology. So very often this outer exterior of this facade of this building is not plastered. So it is just left exposed, and it is possible due to even though the weather conditions may be harsh, but there are no problems because reinforcement is fully embedded and there is no possibility for corrosion in this type of construction. In many cases, the blocks are manufactured with fly ash, and 20% up to 20% of fly ash, which is good. This is interior of a building, again, not plaster. It is exposed. It's considered to be an architectural features to have exposed the blocks in the same way as in some cases in India we have exposed bricks, which also looks nice. So this is exterior. This is also additional layer of masonry exterior, which is so-called veneer. It is like a facade element on top, in additional layer, which is non-structural in masonry buildings. In Chile, for example, I've seen examples of reinforced masonry with hollow clay blocks. So they would look the same as concrete blocks, but they're made of clay. In Chile, they mostly use confined masonry, but I've seen also examples. So in some Latin American countries, even though confined masonry is prevalent type of construction, they also use reinforced masonry with, in some cases, with clay blocks. But such blocks, I believe, are not available currently in India. on the large scale, or maybe they're expensive. So that to conclude about reinforced masonry, it's a very good form of construction if the type of masonry units or masonry elements are available. If they're not available or are not of good quality, as we will discuss tomorrow in discussion of masonry materials, right now in many countries there is a tendency to use concrete blocks, but they're like handmade, or not handmade, but made at small scale facilities without proper conditions for manufacturing. They will lead in a poor strength of masonry construction. So for that reason, unless and until there are good large-scale plants, facilities for manufacturing, it is better not to use reinforced masonry in high seismic zones. That brings us to confined masonry. This is the last part of this lecture, and this is an introduction to confined masonry, to define confined masonry. If we were in a classroom, I would ask how many of you know about confined masonry or have seen a confined masonry building, since the code has just been issued in India and there were no many prior examples of confined masonry. Probably few of you have a significant background, but you might have heard, since there has been a publicity in India regarding confined masonry, I would say for the last 15 years. I myself have published the first monograph on confined masonry through NICE, National Information Center of Earthquake Engineering, which have published also the several other confined masonry publications. I published that monograph in 2007, so it is 15 years ago. I believe that was the first confined masonry publication in India, or at least a larger publication. So confined masonry is a construction system where walls are, it is load-bearing masonry system, same as unreinforced masonry, same as reinforced masonry. In that system, walls are constructed first, but there are reinforced concrete column-like elements and beam-like elements which are cast afterwards. And these are some examples. These are just graphic examples by a publication by Tom Schacher, which is also available in a graphical publication, which is available through NICE. So on the left side, we can see confined masonry structure where you can see masonry walls. And then you can see in the corners and the specific locations, this confining reinforced concrete, vertical confining elements with reinforcement and the concrete. And whereas in reinforced concrete frame construction, and we'll discuss this difference between the two systems at the end of this lecture. First, we construct reinforced concrete frame, and then walls, masonry walls are infills, merely infills to the frame. So that is a different sequence, and it's entirely different system, even though they may look alike once the construction is finished. So reinforced concrete frame construction, this is an animation of the so this is how it looks like. And then for confined masonry, reinforcement has to be constructed at the beginning. And this is the foundation level, plinth band, and then masonry walls, followed by reinforced concrete in tie columns, and then tie beam, the element, horizontal element, and then slab. So it is each floor by floor, the construction progresses in this manner. Key components of confined masonry building are masonry walls, which are made either of clay brick or brick or block units. It could be clay or fly ash, whatever is available. The tie columns, which are vertical reinforced concrete confining elements, which resemble columns in reinforced concrete frame construction. Tie beams, horizontal RC confining elements, which resemble beams in reinforced concrete frame construction. Here is the example how a confined masonry building in India will look like. There are certain rules where vertical confining elements are placed, as we will discuss. But you can see that this would be different than in reinforced concrete frame construction. You can see that there are some vertical elements of this wall between the window openings, and of course at the corners, intersections of the walls. And horizontal elements are provided at the floor and the roof levels, but also at the lintel level. This is not common in other countries, but in India, because of the long history of lintel of the bands in the code, lintel band is and twin band in some cases are always present, are present and prescribed by the confined masonry code, as you will see. So how did the construction of confined masonry start? How did it start? What are the beginnings? It evolved through an informal process, which is based on satisfactory performance in past earthquakes, so good earthquake performance. It was not designed, developed by engineers. The first use of confined masonry was after the 1908 Messina, Italy earthquake, which had magnitude of 7.2 and killed about 70,000 people. And at that time, it was used in the construction. But what happened is that in the area of Messina, there were some confined masonry buildings before the earthquake. Excuse me. And they did not collapse. So that is how it was first observed, and when it was first observed. Afterwards, it was observed, it was somehow, the technology was transferred to Latin America, and it started to be practiced in Chile and Colombia since 1930s, and Mexico since 1940s, and then in other countries. So it is very widely used in Latin American countries, which are also very prone to earthquakes. So currently it is practiced in countries and regions with high seismic hazard and risk, including Latin America, Mediterranean, Europe, Middle East, for example, Iran, Indonesia, South Asia, and the Far East, which is China. So they're all, China has, for example, a code for confined, which includes confined masonry for many years. And many of these countries have codes which have been in place for many years for confined masonry. Some examples, this is example of confined masonry building from Mexico. You may not be able to see, you will be able to see on the slides, but maybe not right now, or maybe you can. Vertical reinforcement. So this is an example with concrete blocks, hollow concrete blocks, but it is confined masonry. And this is example from El Salvador, where it is one of the rare countries where they have band at like tie beam at the sea level. It is usually not common in at least Latin American countries, and it's not prescribed by the codes. This is from, I believe, from Iran, also confined masonry with bricks. And this is from Indonesia. In Indonesia, they've been using confined masonry since 1980s. It has been exposed to many strong earthquakes in that country, including the 2004 great tsunami and earthquake, and it was performed well. They use thinner walls for confined masonry, but they mostly use it for 1 to 2 story single family buildings. They don't use it for taller buildings, so therefore walls are very thin to be economical. These are some examples from Chile. Chile is a country which widely uses confined masonry. On Friday, I will show, there will be a separate session on performance of confined masonry buildings in earthquakes, and I will show quite a few photographs from Chile, which I visited after the 2010 Maule earthquake, which had a magnitude 8.8, and where confined masonry was used. And the result of this earthquake was a very small death toll of only 500 people, and out of which whom 100 died in tsunami. So very few people died due to confined masonry building collapse. So it performed really well in that earthquake. This building is on the left, is also a confined masonry building in the Santiago, capital of Chile. You cannot see confining elements, but it has a facade elements on top of masonry, so that's why it cannot be seen, but it is also confined masonry. On the right-hand side, you can see apartment building where you can clearly see location of confining elements. These are both photographs from Chile. And as I said, already performed really well in this February 2010 Chile earthquake. And I believe that you also remember same year, 2010, but in January, in magnitude 7 earthquake struck Haiti, which was caused the death toll is not confirmed to date, but it is more than 2 to 3 lakhs of people died in that earthquake. In other countries, Latin American countries like Peru, a similar performance of confined masonry has been observed. This is an example of a confined masonry building that survived the 2007 Pisco earthquake, magnitude 8, where the surrounding unreinforced masonry buildings collapsed. Some layout rules, I will skip this because we will be talking about that in the following lectures, but maybe just as a first introduction, as I mentioned, for confining elements, we need to have certain spacing, and this is also part of the code. Maximum spacing of these tie columns, no matter whether there is another wall or not. So maximum spacing is less than 4 meters. Then tie columns need to be placed at wall intersections, at wall ends, and openings as well. So these are some rules which have to be followed in order for a structure to be considered a confined masonry. Otherwise, we cannot call it confined masonry, and we cannot treat it as a confined masonry structure. So confinement at the openings, at the ends of the openings is critical, as well as the other locations. This is another diagram showing confined masonry. It's originally from Mexico, for Mexican code. They have this graphical representation, and this show, you can see horizontal tie beams which are at each floor level. In Mexico, there is no requirement for any other tie beams except at the floor level and roof level, no requirement at lintel level. And there are rules, and we'll talk about that when we talk about section on construction or detailing of confined masonry buildings later this week. What are the rules, and as prescribed in the code, in IS code, related to the thickness of the walls, minimum height to thickness ratio of the walls, and so on. It has all been prescribed in a similar way. As I said, if we have a confined masonry wall which has only confinement at the ends, but we have a very large opening, which is more than 10% of the wall, of the area of this wall, and we call a wall or wall panel the one that is enclosed at confined on all sides by these confining elements. If there is no confinement around large openings, then we don't consider this wall as confined. If we want to consider it as confined, we need to provide we need to provide the same vertical confining elements as at the ends. So this effect of confinement at the opening has shown, was revealed or confirmed in past earthquakes, and the buildings that had no confinement at the openings but had these confining elements in the middle because there was another wall in the other direction, there was more extensive cracking and damage. Not necessarily collapse, but there was more extensive damage than in the buildings that had confinement. On the right-hand side, even though it was not visible, this was a building which was exposed significantly to the 2010 Chile earthquake, and it had confining elements at the openings and performed well with some cracking, which is understandable given the size of the earthquake. Another feature of confined masonry is toothing. Toothing is interaction, enhanced, I would say, joint action between the concrete and masonry in confined masonry walls. There are horizontal toothing elements are like zigzag, and in brick masonry, it is possible to extend some of the bricks in a zigzag manner, and it is like teeth. That's why it's called toothing. So it is a small dimensions, something like 2.5 centimeters. It is it requires some a bit of complexity in construction, but in the beginning. But once there is practice, it is easier over time. And then, so in that case, when concrete is cast, it forms some form of shear key between the masonry and concrete. This, of course, is not in place in reinforced concrete frame buildings where you have a flat, since concrete columns are constructed first, you don't have this tooting. In some, if instead of bricks, blocks are used as a masonry unit, it is not possible often to create tooting in the same way as in bricks. But in that case, it's possible to place horizontal reinforcement to cross this interface between the concrete and masonry, and that is an alternative to tooting. This is called shear connectors or dowels. So in both cases, this is some form of shear key, which is shear enables better action or joint action of masonry and concrete in this form of construction, confined masonry. This is example from Mexico. You can see that this is concrete block. There is no tooting, but there would be a reinforcement going from the joints and extending into these tie columns. And this is in Chile. You can right-hand side, you can see horizontal reinforcement and tooting. They, in some cases, they use both. These are examples from India. We will be talking later this week about first application of large-scale application of confined masonry in India at IIT Gandhinagar campus. I believe many of you are from Gujarat and can visit the campus. Unfortunately, construction is over, so these are some photographs that were taken during the construction in the period of from 2013 to a few years ago. There was a construction of confined masonry buildings on the campus, and these are fly ash bricks, and you can see tooting that was achieved in confined masonry walls in the entire campus that was constructed using confined masonry. These are diagrammatic or schematic, very nice schematic diagram of confined masonry walls in Mexico, where they showed where confined masonry elements are used. This is from one of the manufacturers of blocks. So they use these hollow clay blocks, which have no ability for reinforcement. So therefore, reinforcement is placed in as confined masonry. So that practice of confined masonry is very well known in Mexico. And you can see here again example of the wall. And in Mexico, for example, they have a special elements which are like used as confining elements where they can place reinforcement. And also this reinforcement cage is prefabricated and can be delivered, ordered. You don't have to be done at the site. So this is an example how they would then provide reinforcing, and this is an example of reinforced masonry, but it is also an example how they would then provide horizontal reinforcement in the confined masonry in situation where there are blocks. So this situation is currently not there in India, but in future it may happen that this type of blocks are manufactured, and in that case the reinforcement may need to, tooting may need to be achieved through horizontal reinforcement. You can see here this cage, so it is prefabricated and it's cut to deliver to size one story high, and it can be delivered. So these bars have been welded to at the plant, and they don't have to be manufactured at the site, which is good. So that is all about confined masonry. As I said, there's no need to discuss it more because we will be talking about it anyways throughout the course. The whole course is about confined masonry. At this point, I would just like to mention what is the difference between reinforced concrete frames and confined masonry. On the left-hand side, the red colored diagrams are related to concrete frames with masonry infills. On the right-hand side, there are diagrams related to confined masonry walls. On the top diagram, you can see the first thing is what we discussed, is construction sequence. And we discussed that already. So that in reinforced concrete frames, the frame is constructed first and the wall is constructed later. In confined masonry, we have a joint simultaneous construction of walls and concrete elements. And first the wall is constructed and then confining elements, but they are kind of constructed together, floor to floor level. whereas in a concrete frame, we have the whole structure, multi-story structure constructed out of concrete, and then walls are constructed. As a result of this difference in the structural system, because in reinforced concrete frame is the main system that carries both gravity and lateral loading. The column and the beam elements are larger because they have a main role in the system, whereas infill walls, unfortunately, are often not even considered in the design or in the numerical models that are used for this simulating behavior of or analyzing behavior of reinforced concrete frames. So these are robust sizes of column and beam elements in multi-story buildings. In confined masonry, the size of concrete elements are much smaller. The size of these tie columns are usually equal to the size of the wall. So if the wall is, let's say, 1 brick thick, 23 centimeters, then tie column is 23 by 23 centimeters. Similarly, tie beams are of similar size. There is no need to have larger elements because this is these tie columns and tie beams are just reinforcement for masonry walls. Here, masonry is infill to concrete system. Here, concrete is just technology that is used because it was not possible to do it in masonry. As you remember, I talked about nominally reinforced masonry and how difficult it is to challenging it is to reinforce brick masonry in vertical direction. This has been a way out by providing a separate element which works together with masonry wall. As a result, finally, the bottom drawings show the behavior. So the difference in behavior on the left side with the concrete frame, there is significant bending in the beam columns and beams, and they are because they're bending moments and significant shear forces in these elements, in addition to axial loads in the columns, for example. And this infill wall, if it is modeled and if it is simulated, its effect of infill walls can be simulated as a strut or a truss-like element in these reinforced concrete frames. In confined masonry, everything works together. You can see that this whole wall with confining elements moves together because it is like a composite. This is a composite structure. It is composite masonry plus concrete structure, and every wall is a composite masonry and concrete structure. And that is how it is designed. That is how it needs to be modeled for any analysis, structural and seismic analysis. So these are the three main differences between the confined reinforced concrete frames and masonry. This is particularly important to understand in India because this is a beginning of implementation of confined masonry right now. All engineering students and engineers and architects are very familiar with concrete frames, and they know how to analyze, design, and construct them, or to supervise construction, whereas confined masonry is a new construction technology. It's a new product on the market, and there is a need to understand the difference. And what is dangerous is that they look similar. It is a good and bad thing. Good thing is that confined masonry and reinforced concrete frames use the same technology, but the bad thing is that they are look the same, and then there is a chance that engineers and architects may say, oh, well, it is the same and I can design it in the same way. Even though now we have a code for confined masonry, I can still use the same approach for designing this system. And that is not true, and it should not be done by all means. That's why education is the key, and that's why you are present and on this course remotely, and hopefully you will spread the word about this. So this is from ERI Confined Masonry Guide, and here I am listing main resources for this course. Main technical resource is the earthquake-resistant confined masonry construction, 3rd edition. I believe you have access to this publication electronically. It is also available for order through, if you want printed copy, by NICE. And it is very nice colored publication I encourage you to order it, but if for the purpose of this course, you can use electronic copy. You are assigned reading based on this lecture. It is introductory lectures, so chapters 1, 2, and 3. The book has 8 chapters, actually 9, but 8 substantial chapters. So 1, 2, and 3 are. It is a light reading. It's not complicated. It doesn't have too many equations. Certainly, chapters 1, 2, and 3 have no equations. It is just an introduction into confined masonry. So this is a assigned reading for tomorrow from this book, and you will have at the end, you will have a quiz, which will also include questions from the book. That the quiz will be on Friday. So you need to make sure to read the book and be familiar with its content. Additional resource, which I believe is international resource, I would say, is ERI Guide, Seismic Design Guide for Low-Rise Confined Masonry Buildings, which was significantly used at the time of development of the code, and many recommendations from the guide are a part of the Indian code. So it is useful to have access to the guide. It is available free of charge. We can also share it through this course, but you can download it at this website, confinedmasonry.org, which is the website of Confined Masonry Network, and contains other very useful resources. I am the chair of the Confined Masonry Network, which is an initiative by the Earthquake Engineering Research Institute, ERI, and has lots of useful resources. So I would encourage you to also visit this site. And if you have problem in accessing this publication, so it is under publications or downloads, and you can that is one of the publications you can download. So these are all materials for this lecture. As I mentioned, thank you. And if you have some questions, I can answer them now, or I could proceed with the next lecture, since the inauguration section and we started, it's normal for the beginning of the course, started a bit later. It's time for the beginning of the next lecture, but I could take a few questions. In any case, I'm ready to stop sharing just to see if there are any questions. So can you hear me?
Yeah, yes, ma'am. Yes, ma'am. Thank you so much, ma'am, for this wonderful presentation, the lucid explanation for each and every topic, a fascinating session, the inaugural session for all the participants. They would have definitely got excited for the forthcoming sessions. And as ma'am said, so if any of the participant is having any question, they can raise their hand and ask now.
Or you can also ask in chat. That would be also possible. So while I'm talking, you can also ask in chat, and then we can go through the chat. I believe that is possible in Microsoft Teams, isn't it? So that could be, we can then discuss some questions from the chat, because I know some participants would prefer to write it rather than ask. So either way is good. And if I don't answer questions during the sessions, I will prepare answers before, let's say, tomorrow, or I would say because my sessions are tomorrow. I have one more session today and then tomorrow. So that is, I would say, from now on. And because it's online mode, I think it's best to ask at the end of the session. So there is one question. Yes, please. Please
Yes,
go
Manish.
ahead.
Very good afternoon, madam.
Good afternoon.
Well, it is before 12 noon. Sorry. Actually, madam, my question is related to. I'm audible to you, madam?
Yes, perfect.
Thank you, madam. Thank you. Madam, in some of your slides, you had shown the blocks, which is now been used in India also, but long back it has been used in foreign countries. The size of the blocks are quite big as compared to the size of the bricks which are used in India, and also the frog space which has been seen in the block is quite large as compared to the frog size which is available in India. So is there any role of this frog size as far as the seismic forces which are actually coming on the wall, and how this, because the reinforcements are being placed on this frog both in lateral direction and longitudinal direction. So is there any role being played by this size to resist the seismic forces, or important role being played in confined masonry?
Thank you for this question. So if I understand correctly, the question is about the comparison of concrete blocks, hollow concrete blocks, which are now also available in India, and performance of clay bricks, which are fly ash bricks anyways, which have frogs. So in concrete blocks, there are no frogs. There is only mortar joint, which is not these are not frogs, these are holes, so I wouldn't call them frogs, so they're holes. And they if the blocks are not reinforced, there is only mortar bedding, so there is no frog. There is no issue with regards to, there were lots of tests done on this type of construction in countries where this is practiced. So there is no problem with regards to the bond between the mortar and the blocks in this, and the concrete blocks in this case. It works well. In case of bricks, so there are frogs, which are used as additional way of means of bonding. So it's simply different technology, and I believe that the practice is that if there is any technology, tests have to be made. So there are tests for bond between the blocks, as well as tests of bond between the bricks. And in the codes like ASTM standards have methods for testing, test setups, and standard way of testing this bond. And it works in the test on the full walls made of these blocks. It works well, but it primarily works well in reinforced masonry, because, as I mentioned, you can consider this just as a formwork to this grouted system, which is similar to reinforced concrete. So if you had reinforced concrete, which is also cast, you would not talk about frogs and bond and all that. So similarly here, the key is to have a vertical and horizontal reinforcement, which is grouted with concrete, practically not mortar. It is microconcrete. The grout is microconcrete, and hence there is no problem with the use. In fact, it is the ductility in terms of the seismic performance. The ductility, it is comparable to reinforced concrete shear walls, even though codes mostly give a lower ductility assignment to it, even in North America, such as US and Canada, but it is comparable really in performance to cast in place reinforced concrete construction. So it is not an issue just because grout is continuous vertically. So you would have, like, if there is vertical bar, it will be grouted throughout the height, whereas in masonry you have bricks, and then you have mortar, and then you have bricks, and then mortar. So here there is more continuity internally in this system, provided that it is reinforced, obviously. If it is not reinforced, then we can talk about whether the bond is adequate or not. But the intention of this system is to be reinforced internally with vertical reinforcement and horizontal reinforcement. And in that case, there is no, definitely there is no question of a bond, or there is no need for frogs. So simply the way we design masonry, and as will be discussed in this course, we look at the design parameters such as compressive strength, shear strength, which is derived from compressive strength. And therefore, if the compressive strength is adequate, which is not related to bond in reality, then we would expect that the system that it can be designed. So it really is not a problem of the bond. It is more a problem or issue. I wouldn't say problem, but the challenge is the strength of masonry of the bricks. And as we will discuss tomorrow, one of the lectures is on masonry materials, where we will discuss required properties of masonry materials. And the main challenge in India with bricks is the strength of bricks. And that is the challenge for confined masonry, because confined masonry is a taller is intended for mid-rise, low to mid-rise buildings, and it requires good quality masonry for application. So I'm not sure if I answered the question, but I could not visualize this as a frog, so sorry if I maybe see it differently than you, Dr. Shah.
Thank you, madam. Thank you.
Yeah. Any other question? I cannot see there is another question, Shashwat?
Yes, ma'am.
Yes, hello.
I just have a doubt, like, what are the...
Yes. I think there is some echo. Maybe, Shashwat, you can send a question in chat.
I just wanted to ask that what are the differences between Indian code for confined masonry as compared to the other countries?
Well, I would say that's a very good question. Every country has different codes, and as you may or may not know, codes are decided by the code committee. So it is based on the global knowledge usually, but also on the specific details of the country. So there may be different requirements regarding the strength of, as I was just talking about, the strength of minimum strength of masonry. For example, in India, there is a difference. When I talk about the code, and I'll be talking following days, I'll give an overview, and then maybe I can give some features that are specific for India. One specific feature is lintel band that is not required anywhere in the world in confined masonry. There is no other code in the world that requires lintel band as a feature in confined masonry. For example, I can give that as an example. Other than that, as you know, research, as you may know, research on confined masonry in India has been limited, and of course, this code builds a lot on the international practice, because that is how it has to be at the beginning with any code. And then as the time goes by and there is more research and more experience with the application of confined masonry, I believe the code will be more and more Indian only, I would say, if I may say so. So, but that is a good question. Yeah, it is different. It is not a copy of any other code. It has its own features, but there are similarities, for example, with Mexican code and, as I said, with this ERI guide. But in terms of the minimum required dimensions of elements, something like that. So it is a combination of Indian experience and, I would say, international best practices, let's put it that way. Or at least that was the intention of the code committee.
Okay, ma'am. Thank you, ma'am.
You're welcome. And I would just like to close this and maybe go to the next lecture, is that one strong reason of having Indian code is that unless we have a code in India, it is very difficult to practice confined masonry. Even though maybe a Mexican code may be more, certainly they have a code since 1940. So it's 80 years of code experience in confined masonry as opposed to 0 right now in India. But you cannot just, as a design engineer or practicing engineer, you cannot just say, well, I'm designing this building according to Mexican code. I don't think it would be acceptable in India. So India needs to have its own code, just like it has for other materials. So same is concrete code. IS 456 may not be as good as, or not good, as good, as comprehensive as American code, ACI 318, and yet, of course, in India, everybody is designing according to IS 456, or same with steel code. So let's put it that, let's think of it in that context and in that way. Code is the basis for starting any or using any construction technology for engineers. Okay. So if this is okay, since we're running, I think, 15 minutes behind, isn't so, Chaitanya? Not so much, and I will go slowly. If my pace is too fast, please let me know. Actually, maybe I can get feedback after this second lecture, because I, of course, have different accent than you, and I tend to speak fast normally. But I try to make it understandable. So I will try to speak a bit slowlier. I was a bit rushing because we started late, so I hope that now next lecture will be at the slow. I will make it at a slowlier pace and the following lecture. So, is it okay to continue?
Yeah, that is fine, ma'am. Yeah. And ma'am,
Okay.
shall we take a break for 5 minutes?